All right, today let's look at a comprehensive review of all of the database cards inside LS-Dyna. Database cards essentially controls the post-processing, like what kind of history variable we're extracting from the model. It is obviously very important, and the thing with Dyna is that it has so much information that we can extract from the model, and sometimes it's just a little bit convoluted. So my hope today is to create a structured review for all of the database cards. I'm gonna update my default database template after this review, as I will demonstrate in this video, and then I'm going to look at a couple of the very commonly used ones that I think every single Dyna analyst needs to understand in order to do their job, really, because you're gonna use these almost all the time. Okay, first thing first, right? So let's look at a table of contents for all of the database cards because what I did was I went to the Dyna documentation and I organized one second organized all of the database cards and what I did was I put them into a spreadsheet format like this, right? So in total there are about about 106 database cards inside LS-Dyna. This is, I think, mostly everything. There's a couple, maybe a couple more I didn't cover in here. For each of these database cards, what I did was I ranked them 1 to 5 based on the frequency and the nature of their applications, right? So, for example, rank 2 are usually specific for a specific type of data card. That's a type of excuse me, Dyna card that's used, and frequency 3 and 4 are for a specific structural and multiphysics problem, and number 5 is for what I consider to be very rarely used. So these will be things that you really don't see very often, that you probably don't need to use them. So that's the way I've organized it, and the reason for that is so I can target number 1, which are these lists of very commonly used database cards. You basically need to use them in almost every single model. Now, some of them are technically can be ranked 2, like this one can be ranked 2. But in a lot of ways, you basically use them all the time for almost all the Dyna models. So when I ranked this, what I did was I put them into a template. So this is the latest revision of my database template card, which contain everything that's in priority 1 in the spreadsheet. And the way I've organized them is that I basically put them into 2 variable cases. One is for history variable, one for the D3 plot variables. And then I added a couple important keywords. This should be commented out right here. These are the things that I'm going to basically use for every single model that I have. And I'm gonna make some basic edits. Okay, so this is what I've done. First of all, is that let's look at the table of content. So if you look at things like here, right, like BNDL, this is usually like very commonly used. You look at boundary condition, force, and energies. So if you want reaction forces, you look at BNDL. YAO, Nodal, RBDL, RC fork, RW fork, RCLs. These are the very common ones that we're using for things like contact forces, nodal forces, rigid wall forces, sliding energy for like frictional contact, to check for penetrations, a SBC fork for basically fixed support reaction forces, and then you have your binary ones such as your D3 prop interface force. Run SF is like a restart file, like a D3 dump file that you can essentially load. Extend info is part of the interface force for the binary interface force. And then database history is a very useful one that's going to be combined with, say, out element output that let you basically determine which elements are being reported in the element output database file, right? So there's a strategy that's put into the code that lets user essentially systematically extract information they're looking for. And what I like to do in this first video is to look at the basic, highly frequently used keywords. Okay, so let's look at these. Okay, so first and foremost is the database extend binary. This one basically controls the content that's written into D3 plot. So such as things such as, so these first two parameters are what's needed to get additional history variables, right? So we use that in a previous video about how to do how to write script that extract, say for example, your first, second, third invariants, and sometimes we need to extract additional history variables. Say for example for glass as well, we need to do that, right? And then if you look at other cards like this, number of integration point is very important in order for us to be able to look at the results, not just in terms of average results from the integration points, but individually on all integration points. So if you're interested in that, this is an option you have to turn on, right? There are different options in here that let you look at specific control for such as, for example, there is a beam IP right here. This number usually need to be higher in order for you to be able to see the results across multiple integration points on a beam element, for example, right? So if you look at the parameter value here, what I've written down here are some common ones. But this card is almost always needed in order to be able to see more data in your result file. The database history card basically assigns a node set or an element set or a solid set or whatever into this database history, right? So this is needed in order to be able to get data into a node out, element out, SPH out, such as these files. So for example, if you want additional information in your node out or your element out, we need to generate a database history and assign a specific set of elements or set of nodes to that to the database history in order for them to show up in the element out. And I'll do a quick demonstration later on to show that. Like I mentioned earlier, BND out is the force and energy reactions. That's going to be at the boundary conditions. So this is a very commonly used one. Basically, everything's going to be written in global coordinate system. So for example, if you want to look at reaction force in one of the boundary condition, like one of the constraints, then you can basically do a BNDR and it will tell you what reaction force it is in the global coordinate system, right? And later on, we can do this in the local coordinate system by looking at how to transform the coordinate systems. And this is the format for what BNDR will usually look like inside the actual file itself, right? So you have the actual nodal groups, and it will tell you the forces in each of the directions. And this is going to be probed out in the global coordinate system. And now the reason this one is in both Y and Z is because I actually rotated the coordinate system just to confirm it's in the global, and it is actually in the global. Okay, so I can actually show it real quick here, right? So in this example, what I did was, if you look at the global coordinate system is here, but you see this block right here is rotated with a part transform, right? And then when I applied a force onto one of the surfaces and fixed the other surfaces, I apply in the local coordinate system, but the result is shown in the global coordinate system in terms of reaction forces, right? This shows you that it is in the global coordinate system. Now you can adjust this back to the global coordinate system by doing the coordinate transformations, and there's a standard way to do that. It is certainly something that we can do if we wanted to do that. And it might be a video that I will make later on as one of the topics that's on my list. Now let's look at element out. Element out is where we can look at things like, stress, strain, and an additional variable that we're interested in on a per element integration point basis, right? So for example, in this case, you can sort of see, right, all of the results are basically averaged into one integration point, and you can see the 6 stress components, your normal stress and your shear stress, right? This is all here, which allows you to do some further processing and further alignment if you wanted to do that, right? So this is a pretty useful way to look at essentially how to get additional plotting from your elements. So for example, I can select a group of elements, and then this will give me this kind of data, and you can sort of see this kind of data is in a pretty decent format, and it's basically calculated at each time step that was specified for each of the element. In this case, I have a single element. That's why it's only have one element, but usually you have a bunch of elements listed in the file. In this case, I only have one element listed. Okay. All right, Nodal is basically for nodal translation rotations. So if you want to probe a node's translation rotations, this is something that you can essentially evaluate, right? So for any node that you have saved in the model, you can essentially probe that node's behavior in the Nodal database card, right? You basically use a database history to find the nodes, save the nodes, and the Nodal is going to show you the translation and rotation of those nodes, which are obviously very useful in certain situations that you want to understand. Nodal forces are based on the force groups, right? And you can do it based on a local coordinate system, right? So in this case, you can sort of see this is the nodal group um, um, uh, for that single element. Yeah, I probably should this screenshot is slightly poor, but the idea here is that you can basically probe nodal reaction forces on those nodes by saving them into a nodal force group. This database nodal force group is required for nodal force to be used. Right, so you use this in combination with database node 4, you're going to generate a nodal force card that look like this. So this one essentially gives you the node ID and the XYZ forces and XYZ and energy of that specific node, and the set ID tells you what that thing is. And we can take a look at an example later on. Okay. And then SLE out, and SLE out is for sliding energy. Sliding energy is essentially, so if it's negative, then you know you have sort of penetration in your contact pair that you need to be looked at. So that's a pretty good way to look at using SLE out. And lastly, interface force is what allows you to look at essentially contact forces between sliding interfaces, right? So I'll be able to show an example in a second. So let's look at interface force as an example first, because I have a dummy model that I made earlier. So for example, if we look at this model right here, right? I have this block seeing a pressure from above, and also is going to be sliding across the plate. So what you can expect to see, obviously, is that you will see a sliding interface force across that block, right? So for example, if I were to show you the interface force right here, if I were to load this, you can sort of see in this case, the block is just going to slide across it. Let me do 30, right? Oh, the reason it's doing that is because I have friction contact there, so it's like it's a single element. That's why you see a reaction force pulling the element in the other directions. Now, if I were to do this, I'll go to File, Open, Interface Force, and I can open up an interface force. And in this case, you can actually probe, say, interface pressure, right? And then you can do this something like 0 to 0.2, right? And then what this will do is it will give you the trace of that interface force going across the block like this, right? So that's a pretty convenient way to look at interface forces. Now let's look at element out, right? So I want to show a quick demonstration of element out. So this is a very simple single element model. I only have one element with 8 nodes. It's a linear brick element with an element formulation of 2, right? And in this case, what I like to look at is, say, for example, the element out. So what I did was I saved a node set. You see this right here? I have a single element. The single element is saved as a name selection with the ID of 9996. When the ID of 9996 is saved, and it's saved right here into a database history solid set of 9996, that right there is going to basically allow the software to write data into the element out database card. So if I look at what that look like, right? So for example, if I go to my example and I show, say for example, I think it's let's look at this one, right? And then let's look at the element out right there. And you can sort of see this element, that's the element out card right here, give you for each element at each time step. These time step, basically the sequence is basically based on how frequently I request it, right? The DT. I can request it much less frequently. In this case, I use the default value of my template, so you actually request a lot. And for each time step, for each state, I can essentially look at each of the element, and there are 6 different stress components, right? And that allows me to say, for example, if I know my group, I can plot the elements based on their ID, and it gives me a decent look at how this whole thing works, essentially, right? So you can actually plot element ID based on plot element characteristics as a function of distance, as a function of time, and you can plot it for this different stress components. So for each of these stress components, you can also calculate other things like stress invariance, principal stresses, and so on and so forth, right? There's no other characteristic because this is a linear elastic material model, but element out give you on a per element basis all of the information you're looking for, and this is the average from all the integration points. So you only have one result from per element because all the integration point results gonna be averaged to this one result, which give you that detailed element by element look. And that data is not going to be available if you don't write it this way. So element out give you the ability to really deep dive into your model to look at specific element behaviors, right? And that's the key here. All right, the other things that's worth mentioning, right? Let's look at, say, for example, Nodal. I showed a little bit earlier about Nodal, so I can also show the example of Nodal here. Right, so I can just show this in the Visual Studio Code. And you can see in Nodal all of the force components of each of the node. These are like the reaction forces of them, not the reaction, sorry, the displacement and the velocity of these nodes can all be probed, right? And these are on a per node basis across all of the selection regions. In a single element study, I only have 8 nodes, right? But in a full model, you're gonna have so many more nodes. So if you're intelligent with what you're trying to post process, a giant Nodal file, you can parse through a giant Nodal file to get exactly the information you're looking for. For example, you can plot a node's y displacement as a function of time. You can plot a y displacement as a function of location based on the coordinate system that you define, right? For example, if you just want to look at the along the x-axis how the element differ in y displacement. If you want to do that, you can basically write a script to parse through Nodal and give you that information that you're looking for. So understanding the nature of the structure of the Nodal, which is why I use only a single element, gives you a very good idea of what kind of data is in here. You can put these data into a NumPy array, and you can do all kinds of operation you want from it, right? Just need to read this file properly, put them in the proper location, and then you can put them in the proper data structure, and you can do all kinds of operation on it that you want, which gives you a far greater level of flexibility in terms of post-processing that you otherwise wouldn't be able to have, right? Okay, so this is basically some of the examples. What I like to do as an agenda in the future is that I have a post-processing script master collection of user-defined functions. What I like to be able to do later on is to gradually add into my master post-processing script, such that I will be able to essentially generate more and more. So this is my general SL template course. So right now I have first invariant, second invariant, third invariant. I have deviatoric invariant. I have an open D3 plot, create result folder, find max invariant, find max second invariant. So I have all of these functions that I've created. Over time, I like to create more and more function to put into this collection, so I can call on it to do various things like we talk about, like processing an LL format. I'll process a Nodal format, right? Or we're looking at other data that's in here in a programmatically as opposed to just relying on a post processor. And that's going to be the topic for future videos. Okay, thank you very much. Hopefully you enjoyed some of this. It's not exactly that fun, but these are very important things to dive into. All right, thanks.